We're now going to look at the rest of chapter 6, and here we introduce the concept of sequences and then series. Just to give you an overview of the chapter, rather than taking it exercise by exercise, I've drawn a little flow chart here where you can see that sequence and series is basically divided into two main parts. So this is really significant. There are two main sections. One section we'll refer to as an AP. Now, the P is another name for a sequence, a very old-fashioned mathematical term called a progression. And so we have a thing called, or a set of patterns that are called arithmetic progressions. And on the other side, we have a set of patterns that you'll recognise as geometric progressions. We usually abbreviate those terms and talk about APs and GPs. So it's really important that you learn the definition for an AP and the definition for a GP, because that will be your first step. When you see a string or a pattern of numbers, you will be expected, or letters, you'll be expected to identify it as being either an AP or a GP. Once we have established that we have, for example, an AP, then there are basically two things we learn about this series of numbers or terms, and that is we find the nth term. We learn how to find, so we might be given a string of 7 terms and be asked for the 40th term. And we have a little formula to follow to do that. The other thing, so again, there's just these two things that we learn about an AP. We learn how to sum up the series. So we've got a little string of terms and we sum them. And so we talk about the sum of the series. Now, I will just follow on because then the only other thing we do is we look at applications. Now, there's all sorts of different applications. I can't really just say all the sorts of questions that you'll get will be, based on one particular, in one particular area, because they're not. You could be talking about building up a brick wall. You could be talking about planting rows of trees. There's all sorts of variations of the applications of an AP. With a GP then, so we've got again two areas that we look at, and not unlike with the AP, we learn how to get the nth term in this sequence. And there's a formula for that, which you'll learn. And then we learn again how to sum up all the terms. And again, there are formulas for those. Now, there is this additional concept we look at only for a GP. So we don't have this concept of a limiting sum. It doesn't apply over here for APs, it doesn't exist, but we will, when we have a GP, possibly get a limiting sum, and our applications are really easy to define. Our applications of GPs are either questions about recurring decimals or questions about money. And then finally in this chapter, there is one more thing we look at, and it is proof by mathematical induction. It only has a very slight association with sequence and series, and I'll point that out when we get there. it's a method of proof, and like I said, it's not specific to an AP or to a GP, but there is a slight connection. I'm not actually going to ask you to do anything out of exercise 6C, because I believe 6C is just an introduction to the concept of a sequence. So, a sequence, what is a sequence? And how you specify them. Some notation about sequences. It says there a sequence of numbers is just a pattern. Now, you've looked at patterns for a long, long time, and you've heard me talk a lot about maths is predominantly identifying patterns. If we had this pattern 1, 3, 5, 7, I'm sure you recognise it, and you could give me subsequent terms in that sequence. Just a few things about notation. You might notice I've got 3 dots there. Let's talk about the 3 dots. They indicate that if they're at the end, that the sequence goes on forever. There is no last term. If they appear in between terms or items in the sequence, then there are many terms we've left out in there. So we're going 1, 3, 5, but we do stop at 99 according to this particular sequence. If we have an infinite sequence, then obviously the dots are on the end. So infinite, dots are on the end, going on forever, whereas finite, definite, then the dots are in the middle, and you can see there's a definite last term in the sequence. Tn is the symbol that stands for the nth term. That's probably nice and makes sense, Tn. So T1 would be the first term. So if we're looking at this sequence, 1, 4, 9, 16, 25, and again you probably recognise that as the numbers squared, then T1 is 1, T2 is 4, T3 would be 9, and T8 would be 64, although it doesn't appear there. Now, just be aware that the first term, T1, may be also denoted using A. So if you see an A appearing, it's just referring to the first term. Not all patterns of numbers are an AP or a GP. There can be other types of patterns, and the Fibonacci sequence is an example. You may be familiar with it, where we start with 1 and add the previous digit, which would be a 0. So 0 and 1 is 1. Now from 1, add the previous digit. 1 plus 1 is a 2. 2 plus a 1 is a 3. 3 plus 2 is 5. 5 plus 3 is 8. 8 plus 5 is 13. 13 and 8 is 21, and 21 and 13 is 34, and so the pattern goes on. Now, the only reason I'm talking about it is because it's neither an AP nor a GP. So just be aware that it is possible to have a sequence of numbers that doesn't fit the families that we are going to be focused on. So we're only dealing with APs or GPs. Now these are really specific. There are 3 different ways to specify it, how we could write it out. So you could simply write out the terms. Write out the first few terms, and if it's infinite, complete it with dots. You could give the formula for Tn, give a formula, and Tn denotes the nth term. For example, if we look at this one here, we could say we've got a series where each term is 3 times n. So T1 is 3 times 1 and T2 is 3 times 2, which you can see works. So write out the terms or give a formula, or where you give an instruction on how to obtain subsequent terms. The Fibonacci sequence is a good example of that. And this is referred to as the recursive formula. So we would say that we would point out the connection between the term and the term before it. So every term is identified as being created by performing some operation on the term before it. Now, that's just recursive. Remember I said that we're going to do proof by mathematical induction? That is a proof that relies on this concept of recursive. Things to note: n must always be positive as it counts the place, and we don't talk about negative places. Let's have a look at the example. Oh,